So, light. It's a function of electromagnetism. What the heck does that mean? Well, you all know what that means. We conjecture
Although
ahead.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be
Instead,
just hyper Rulial Turtles All the Way Down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So, yes, we are back yet again. I'm running behind on some things, but what else is new? But as we can see here, yes. For our thumbnail, brought to us by space.com. What is the speed of light? The speed of light is the limit of the universe. Or is it? Thank you for your contribution. Yes, we're obviously going at the speed of Ultra Instinct Omen Goku. Thank you. Hey, I love listening to a little bit of a backtrack. But I digress. All right, let's go back to the one thing on the Wolfram Alpha's blank impedance. What the heck are we talking about? That's what we were talking about yesterday. It's a lovely story. I'm not actually going to answer the real question, what is electromagnetism a function of? Number one, I don't know. And number two, it sounded really cool, and I was playing around with, we'll get into that in the future. I think you guys are going to like it. Electric impedance. What is this thing here? We have 1 over 4 pi times the speed of light times the electric constant. Gives us this thingy right here. That's the thing that we derived a couple of pretty cool terminal actions. We're using the Joe 1 times the 3n, basically 15 over the domino tiling constant, and it hits it very well. But we will get into it in just a moment. Okay, thank you, Wolfram Alpha. The Wolfram Cloud. Yeah, links are in the doobly-doo below. Not the Ultra Instinct thing. I apologize, because it's only playing for me because I'm greedy. I don't think the track really felt. I also always get like blocked in Japan. But, alright, so what are we talking about here? Let's go. This was the original notebook that I've been working on that I needed to recreate after it. Long story. So the speed of light, and back again. An Ohm's tale. Part 2. So speed of light in a vacuum. People may argue upon what vacuum means. That's another story. As we have here from a total screenshot of a version of 44 that I've probably done a couple times. But C, the speed of light, is equal to the Planck length divided by the Planck time. A unit of length per unit of time. Imagine my shock. Times our terminal boundary, because that gets us out to 7. We know the speed of light to 9. We multiply it by 1 plus the square root of the Giesecke constant. That happens to be a minimal manifold for 3 dimensions. Nifty. Times Joe 1 minus Joe 2 times our inversion boundary there. What the heck does that give us? It gives us this number right here. What is this? This is 2.997924580. Oh. Well, that's like 9 significant digits. We only know it to 9. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or you could call that 9. Please to be a geometric derivation of the speed of light, but we've done that before. That's fine. We're going to move along in our little document that, again, is available in the doobly-doobly-all, in case anyone wants to follow along or check the receipts, as the kids like to say. All right, our inversion boundary. It's at approximately 1 ampere. There appears to be something going on right around 7 significant digits. Shall we? Oh, we shall. So what do we have here? This is our inversion boundary. What the heck is that? Well, it's just the value for the Planck mass. The Planck length. Oh, it says freaking meters. I usually do it's okay. It's communicative. And I believe associative. So in this dimension, it works. Planck length times the Planck mass over the Planck charge squared. Boom. We get this. We often, and I myself has been using this, I just put like, I don't know, 10 to the negative 7, because it's a 1. It's not exactly a 1, which in itself is also interesting. At least according to our calculations. Could be wrong. But right around 7 decimal places, 1, 2, 3, 4, 5, 6, 7, things seem to get a way bit wonky. So, as we go along, okay, so what do we have here? All right. It's approximately 1 ampere constant. You want to do constants because amperes will give you a different value in Wolfram alpha. I'm just saying I make these mistakes. Welcome, Upcycle. Thank you for joining, my friend. We're just gonna wrap up this part 2, and then we'll see what happens. But what do we have here? Okay, so this is 1 over that. So this is an inversion of our inversion boundary. You see what I did there? Ah, yes. So we just put a 1 over that. You can just put this all in Wolfram alpha. Heck, you don't even need to do it. Just do a little Planck mass, Planck length over Planck charge squared. You just even raise the last one to negative 2, so it just puts a denominator for you. These will say, hey, neutrino. Thank you for joining, my friend. But it's literally to a point, and again, I am not a professionally trained physicist nor a mathematician. I am a dude on the internet that's crazy enough that moves like 2,300 miles out here to frickin' Utah to take part in a frickin' monastery. Why? Number 1, I am a crazy person. Number 2, my dad, Mr. Means, God rest his soul, he was an attorney. He told me to look for evidence. I've seen enough evidence to have me come out here for like a year. Just personal opinion. Again, crazy person. Every once in a while, crazy people are right, though. But, okay, so what do we have here? Okay. That inversion gives us this. And I'm like, I don't know what any of this stuff means. And I looked at this number here. I'm like, 157.9 something. I'm like, this number looks familiar to me. I think it had something to do with pi or something. And who doesn't like pi? So what did I do? Well, that's kind of a big number. Let's divide it by 4 pi. Divided by 4 pi. And then I got this number, and I'm like, oh, I know this number. I think I may have just used it. So I divided by 4 pi again. And I broke something in the notebook. Oh dear. Oh, what's this? Comes out to approximately 1 magnetic Coulomb constant. To 1, 2, 3, 4, 5, 6, 7, 8. So like 7 or 8 significant decimal places, depending on where you want to put you. Yeah, it's the 1 or the 9s. It always confuses me. And I'm like, that's very interesting. Magnetic volume, susceptibility. But, okay, that sounds like something electromagnetism with the magnetism. I'm like, okay. Just for easy notation, so you don't go crazy with the numbers, because the numbers scared me. They scared me so much, and then you realize, like, not saying that Professor Wildberger has kind of said that. He gave some crazy article about, like, real jobs, real toaster fish, and yada yada. Real numbers are very interesting, especially since they're called real. Just saying. All right, so 1 over ampere constant. You want the constant in there. You just type this into Wolfram alpha. The funny thing is, even in Wolfram alpha, what? Why doesn't it just say 1? That's really close to 1. It's not quite 1. Basically, it gives us those same, more or less the same magnetic things going on there. You divide by another 4 pi. Divide by 4 pi, 4 pi. Or at that point now, you just do 4 pi squared. And it brings you right down. Groovy. So, this is technically supposed to be another story. I know. I've been playing into the story. So what are we actually talking about here? We're talking about the Planck impedance. What the heck is that? That's what we were talking about yesterday. That's basically our ohms. Our ohms. AKA, what is it? Thank you, Wolfram Alpha. Kilogram meters squared per second cubed ampere squared. That crazy thing right there. Again, notation would never confuse anybody. Confuses me all the time. All right. So we do that. We throw in our dimensional characteristics for the impedance because here's how you check. You could express all those as essentially one. What are we doing here? We added in one ingredient of mass, the blank mass. We add in two ingredients, the length, two of them, because it's squared. And then time, here's where it gets a little tricky. This throw me off a bit for a while. You want to have 3 times, but you want them in the denominator. So you raise it to the -3. And then current, here's the actual tricky thing. Because at least within the monastery system, we're using the 5 units, because from them you can derive everything else. So current, if you see this on Wolfram Alpha, you just express it. It's a derivative. Basically, it's just blank charge over time. Charge divided by time. What is that? That's just this right here. See? You throw in the number that you, again, in the dimensions, it's just 1. So you throw 1 there, divide by one of those, and then you just square it right there, and that gives you your 2. And since you have 2 of them and you want in the denominator, you raise it to the -2. Savvy? Okay. I still messed that up. Okay, so blank impedance that we calculated yesterday using 15 over the domino tiling constant. That's kind of how you would lay out, let's say, a bunch of dominoes, and you don't really want them to overlap and stuff like that. I am actually not exactly sure of the parameters. I know it just pops up an awful lot, and if we're going to try to do something to construct a tiling of, I don't know, existence or something, might be useful. Just an opinion. I'm totally biased. But, and we multiply that by Joe1. That's basically from the hyperbolic vortex, hyperbolic Mobius partition function, I like to call it now. Call it whatever you want. Hyperbolic vortex equation, the 1 over 1. 1 over x plus x cubed divided by 2 pi set equal to I raised to the I, and that's all raised to negative pi divided by 2. So like a little twist, and then you just subtract off the lambda, which happens to be the Planck mass. And you can actually just do not even the calculated derived Planck mass that we claim. You can just literally use the Planck mass, the 5 significant digits on Wolfram Alpha, and then you square the first answer, and you get the fine structure constant, at least according to Wolfram Alpha. Okay. Side rant aside. Hey, Gap, what's going on, Purple? Hey, how you doing, my friends? And again, I'm just doing a little bit of ranting about stuff today, because again, don't worry about the numbers. It's just some stuff doing some things. Why? You could do the same thing for cooking and stuff. If you want to measure up every single molecule of flour, your head's going to explode. It's like, hey, just think about this much flour and you do this. So, okay, what were we talking about here? Okay, we had, so we had our construction, our dimensional ingredients, which in this case are mass, length, so space. So you got some stuff, you got some space, you get some time, you get some current. Bada boom, bada bing, you add in the geometric terminal action here, and that's how they blend together. And then we get, what is this? Yeah, so it comes out of Planck impedance going to Wolfram Alpha. It's 582. We had it to about 7 before. Okay, so 5, 8. It's a 1. I am off. You are very correct. What are the next 2 digits? Oh, 9, 9. Again, I'm not a professionally trained physicist nor a mathematician. But what I learned in grade school is often if it's over 5, you round up. I'm just saying, might there be the possibility to our measurements from our instruments that we now have to like 10 decimal places, at least according to like the Kodak update for certain constants that may or may not have been adjusted. But I'm just saying, could we consider that a 2? I know that's asking a lot. It looks like a pretty good geometric fit. Just saying, just saying. That's all. We continue. All right, what is this? How are we going to go back? All right. The speed of light equals the Planck impedance times 1 over our inversion boundary. Oh, that was that length mass divided by charge squared. All right. So you do the 1 over that, and then you get that, like, all that 157 magnetic coulomb, those two spheres, or 4 pi squared, whatever it was. All right. So we throw these ingredients together. I got lazy in it. Sometimes when it's calculating the units, you don't want to confuse it too much, so we're like, all right, our calculated value we just did for our ohms, and we multiply by 1 over our inversion boundary. And then I'm like, because I was looking at some of these, I'm like, what happens if I combine these things? And I saw Dad doing digital wizardry, like cancel this out, and I'm like, wait a second, I think that comes down to like length and time left over. It does. Wait a second. Wait a second. This is 2. Wait a second. No, that is. I have this wrong, don't I? How did I put that in there? I put ohms. Is this the speed of light? No, that's not the speed of light. I need an extra decimal point. Oh, I saw the 8 and 0, and I assumed it because it actually should be equivalent to what we just calculated. Oh, that's an error on my part. I apologize, everybody. It should be 2. Oh, where is it? 458. 458. We didn't have 458 there. 4 5. Oh, did we? Where did we get it over to? 4 5. Oh, it is right. I apologize for apologizing. I guess I was right there. Again, maybe I completely missed that. I think it was the extra digits that kind of threw me off. I haven't looked at this that much. I apologize. All right. Oh, so going back to what we were just talking about, what is this? No, that's not what I was looking at. That's a geometric derivation of the speed of light. Yeah, no, this is wrong. Okay, never mind. That was about the speed of light. I need a terminal action or something for that. So that's actually very interesting right there. I apologize. Okay, some other cool stuff and things real quick. But yeah, 500 significant. Hey, right now the model we're looking for, it's 14. The reason why it's 14, why? They're trying to like bridge quantum mechanics to general relativity. Coincidentally, I think it was Professor Green at one point said, yes, as far as gravity comes along, it's like Newton came along and he gave us 7 significant digits. And then Professor Einstein came on the scene and he gave us 7 more. It's like you sit back, it's like basically the Einsteinian kappa that we claim to know. We know to like 13 or 14 significant decimal places. So that's usually, if available, we use up to 15 or more. I usually use a butt ton more, sometimes like 20. That's why it doesn't always work on Wolfram Alpha. But basically, you want to have as much precision as you, and that ultimately real numbers. If you need to calculate the square root of 2 all the way, technically you need to do it forever. That's why real can be kind of dubious. If we're doing analysis, like you said, I think 500 is usually pretty good for most of our things. Not all. Sometimes you need a lot of terms. But it is very interesting. Okay, so some other cool stuff with things. What is this? This is meters per second times our inversion boundary there. Kind of like we were just doing there. Yeah, it gives us that. Oh, God. I'm sorry for the jumping around. Okay. Stop interactive rendering. Okay. I think I fixed it. I'm sorry, I'm a noob. I'm noob to publishing stuff, so. Okay. No, stop. But okay, so we go back down here, and okay, so this is just with the dimensions. Length, time. Boom, you add it. Comes pretty close, has the dimensions of the ohms, but it doesn't quite have the same magnitude, which is interesting. So we take our calculated speed of light here. We literally plug that in, and now we're just going to do 1 over the ohms. Oh, look. Wait a second. Speed of light times impedance gives us that magnetic Coulomb constant values. Oh, so it's like the 2 4 pi's. Like the two spheres are 4 pi squared of magnetic Coulomb constants. That was pretty cool. Let's try 1 over the speed of light. And we'll multiply it by those ohms. Look. This looks pretty damn close to, oh, their inversion boundary. It's right around 1 ampere constant. Magnetic permeability? Wait a second, permeability? What were we talking about? Susceptibility? Might there be a bridge between the impedance of our existence and the speed of light itself? I mean, I don't know. I'm just looking at some of this stuff, and I think it's pretty neat. So that's all I really got for right now. So hey, take care of yourselves, everyone. It's a wacky and wild world out there. All I know is my personal opinion. I think most folks are good people. Good people can figure these things out. Why? Because we can. I mean, we could destroy ourselves, but that seems kind of like a boring story. Just the opinion of a dude on the internet. Peace out, everybody.